Greetings all. Here we go. We are going to talk about the last thing in this unit. First of all, those of you listening today would recognize that we were supposed to have a quiz today, so you have a quiz in the log. Take that. We'll talk about that at the start of class next class period. You have a review assignment, so you can start practicing towards getting ready for the test, which will obviously still be scheduled for Monday after this weekend. And then in addition to that, we have one more new thing to hit, and that is, it's a new old thing. It's the same thing. At the very end of every chapter, we've been doing rotation. And rotation is always analogous. So if there's regular momentum, which we call linear momentum or translational momentum, this is called angular momentum. And angular momentum, if regular momentum looks like P equals mv, which is momentum equals mass times velocity, then angular momentum is L. I don't know why I use the letter L. I actually do not know. But mass in our land of rotation has been inertia, right? That's how hard it is to turn something. It's called inertia. And then instead of a V for velocity, we use an omega, meaning, or a W, meaning angular velocity. And it works just like before. Angular momentum is conserved. The universe wants to keep it. Okay. Proof of that is a basic child's toy, a good old-fashioned top. If you have a top, let's see if I can draw a top. No chance. Well, I tried. And it's spinning. Why does it stay spinning? If the heavy part's up, it should fall down. In fact, when it stops spinning, when it runs out of spinning because it's had too much friction, what happens is the thing falls down because it no longer has angular momentum, trying to keep it in the same position. Okay? A better example of this is one you're even more familiar with, and it's that crazy thing your parents told you as a child. They said the following. They said, you need to, when you first learn how to ride a bicycle, you need to pedal faster. Now remember, when you're first learning out how to ride a bicycle, you might be thinking, of all the crazy things you don't want to do, pedaling faster seems like a good way to die. Right? Okay? So your parents said, no, pedal faster. That's the best way to learn how to ride a bicycle. And it turns out it works, right? Because the moment you pedaled faster, suddenly you could ride your bicycle. In a better example of that, you can imagine if you're stopped at a stoplight, really good bicyclists will manage to kind of wiggle back and forth and keep from falling down. But kids just learning how to ride a bicycle and put their feet down. Why? Because when the wheel is turning, okay, you have angular momentum. Therefore, you have a desire to stay upright. Okay? The moment you stop spinning your wheels, it's much harder to stay upright, and therefore you're going to fall down. Okay? And so again, the idea being that there's a natural desire to keep spinning. Now I'll show you a class example that later on. You need to ask about the ghost of Amy, and I will show you the ghost of Amy, and that will help you understand this idea even better. Okay? Okay, so we got the formula. The basic idea of the gyroscope is many devices, if they want to know where they are in the world or where they're related to the ground, like airplanes, okay, what they do is they set a top spinning with a big old heavy metal band around the outside and then just a little thin narrow thing. It's basically a top. And then they put it in a rotational, something that can rotate in 360 degrees. So when a plane starts to tip, the gyroscope, wanting to keep angular momentum, will stay flat and level with the terrain, right? So once you get spinning level to the terrain, it will always tell you where level to the ground is, okay? And so you can use a gyroscope to make sure you're there. And they use them in missiles, use them in planes, they use them in submarines to figure out where you are relative to the Earth. Because once you get the thing spinning right, it wants to stay spinning right and will force itself to be so. Now, angular momentum has one really different property, and the really different property has to do with the fact that inertia isn't mass, which means you can change it. Remember, inertia is how hard it is to turn something. And when we had that demo in class, we had that stick with the two masses on it. Now, it was much harder to turn when the masses were out than when they're on the inside. Okay? And so when you have, so inertia is much higher in the first case. Okay? This is high inertia. And this is low because it's harder to turn something when the masses are farther from the center. In fact, if you just think about it, they're moving farther, so it takes a lot more effort to turn them, right? To accelerate them. Now, why is that important in this case? Well, because unlike regular momentum, where you can't change your mass, you can change your inertia simply by moving your arms in to your body. Okay, example of that, the classic example of that is an ice skater. An ice skater, right before they go into a jump, you will see them do something fancy where their arms and their legs are as far apart as they could possibly be. Then when they go to do their jump, they turn and then they bring everything in. Right? They get their arms and legs really tight together. Why do they do that? Because in this case, I have high inertia, right? In this case, I have low inertia. So look at your formula for momentum, right? If I lower my inertia, my angular speed goes up. And that's why when you see a speed skater, not speed skater, a fancy ice dancer, what are they called? Ice skater, pull in, when they do that turn, they pull everything in because they suddenly will go faster. Okay? And by the way, they can control how fast they're turning. So if they're spinning and they're going a little too fast, you'll see them kind of untuck a little bit. They lose points for that, but at least they don't fall on their bottoms, right? And if you so they can vary it that way, right? Because they can vary their angular momentum just by simply moving their arms in or out. Okay? Hopefully I have a chance to show you that in class as well. Not that we have a lot of ice dancing available. Now there's also another form in this chapter. It's force times time equals mass velocity minus v naught, and that's our inertia formula, something caused by an outside force, not inertia, sorry, impulse formula. And so this becomes, in angular land, force, the analog to force is torque, right, times t. Mass is inertia, and then we got our w's again because we have velocities, right? And so that's inertia times final velocity, initial velocity. This is torque over here. Okay? And that's another formula that pops out using this analog. Okay? Now, we won't use the second one very much at all. In fact, it hardly ever comes up in any circumstances. There are ways around it. But the momentum one, this angular momentum one, we will definitely want to use this. And then it works just like the other one. If I have two things spinning and I drop them onto each other, you do momentum before equals momentum after, the same game. And again, the only weirdness is the fact that since I can change my inertia, sometimes I can use this formula to predict my final angular velocity by pulling in my arms or putting out my arms or something equivalent thereof. Okay, so the examples we have here, we have two example problems. Okay, the first one, number one, a diver shown can read it. So a diver, when a diver's trying to go in the pool, right, remember they're trying to go in straight. I don't know if you've ever seen Olympic diving, but they're probably trying to go straight. So when they jump off the diving board, they start off with a slow spin. And then they pull everything in, and that makes them go faster. And then at the very end, they untuck and try to spear themselves in the water. To do that, they have to time when they untuck, because once you untuck, you're going to slow down your rotation. Okay, so in this case, the problem says, let's see if I can find my spot. Okay, here I am. Okay, so then it says a diver diver such as one is shown, can reduce and increase from their tuck position is her moment of inertia trying to go too fast by a factor of about 3.5 times, okay, from the straight position to the tuck position. If she starts rotating at 8.37, that blank spot means radians, right? Radians per second. When in the tuck position, what can she get? What can she slow her angular speed to when she hits the water? Okay, so her momentum is not changed. There's no outside torque pushing her, spinning her, making her go faster or slower. So we've got I omega has to equal I omega at the end. Okay, so we don't know where initial inertia is, so we're going to put I out here, and we're going to put a little knot down here because that's her tuck position inertia, and she's going at 8.37. Then afterwards, she's got 3.5 times that. I don't know much, but I'm going to write 3.5 times I. Okay, and then I'm going to put an omega off the back of this. Now, fortunately, because both of these are in terms of I can divide that across, and I get omega equals, oh, I need a calculator. Do I have a calculator here? Yes, I do. Excellent. Calculator ready. Not completely unprepared for class. 3.5, and I get 2.3. Where's my pen? Here's my pen. 2.39. Now it's angular velocity, so that I'm going to write radians with leaving a blank spot per second, and that's how much slower I'm rotating when I come out of the tuck position. Okay, same sort of problem on the bottom. Okay, it says a figure skater can increase her spin rotation from initial rate of 1 revolution per 2 seconds, which we're going to change into radians, to a final rate of 3 revolutions per second. If her initial moment of inertia was 4.60 kilogram meters squared, what is her final moment of inertia. Okay, so we're going to try to find what our final moment of inertia is. So same situation, we're untucking rather than tucking. So L before equals L after. So I've got I omega equals I omega. Now we got a little bit of a trick here. We're going to have to figure out what our speeds are. So 1 revolution is 2 pi, so I got 2 pi per 2 seconds. And so that's going to give me that my initial velocity is equal to 3.14 radians per second. And then later on, my final velocity, it says, according to this, is equal to 3 revolutions per second. So that would be 3 times 2 pi per second. That's 1 second. So that would be 6 times that. 6 times pi, and I get 18.8 is my final amount. Can't find my pen. There it is. 18.8. Okay, and so my inertia initially, it says in the problem, is 4.60 times omega, which is 3.14. And then final inertia, I don't know, but I'm going to find that, and 18.8. So I'm going to divide that out, and I get 4.6 times 3.14 divided by 18.8, and I get 0.76, which is what the answer key says it should be, so that's some good news. 0.6768 kilogram meters squared is my inertia. Now, how the heck do you turn your inertia from 4.6 to 0.76? From there to here, how did I change my inertia like that? The answer is pull my arms in, right? Pull in your arms, and therefore you would tighten your mass, which means it's easier to turn you. Got it? All right, so you have some problems to do on 6-9. So go ahead and do some problems on 6-9. And